guess everyone is finished with the Omicron amplifier, outputting the voltage and current. So this morning we're going to keep reviewing I/O a little bit, and we'll do some digital I/O. And after that, I'll show you the agenda here. So we're on day 2 now, and we're actually going to finish up the day 1 afternoon. So we'll do digital output and digital input, and then front panel GTFDI. I guess I'll review a little bit about this, but when Dean starts the training later, he'll be doing a lot of things with the GTNet and GTSync. I guess I'll go through this quickly as well. And so for this morning, we have the cross-rack transmission line and cross-rack transformer. So that's to show how we can have a simulation case that runs on 2 racks at the same time. So we'll modify one of the chapters that we've already done to be able to use those. And then I think after that, we're going to skip to day 5 morning and do a bit of C-Builder after that's done as well. So we'll start by doing digital output and digital input. So we're going to build a small case, and I'll make a new case. So I'm going to have a look and see where the digital I/O cards are in the simulator. So if I look at my config file, I can see they're here on rack 2. So they're connected to rack 2, PB5 card 1. Both of them are on port 2. So I'll just build a simple case. Control section again, you can look in I/O components, and these are the 2 digital cards. So I'll take first of all, I'll take a digital output, and I'm going to need one of these processor assignment blocks. It's a good idea to always use one, even though it's on PB5 card 1, so we'll automatically compile the controls processor to card 1. So we shouldn't have a problem, but it's a good practice to use this block. So we'll assign controls processor 1 to card 1. So inside the GTDO digital output, we have 4 options. Instead of having 64 inputs to it, we just have 4 inputs, and each of them are a 16-bit word. So we'll only use channels 1 to 16 for now. Fiber port number, anyone remember what it was?
2.
Yeah. And how about this one? The 7-segment display number. Should I change it or should I leave it? Two? 1? Which one? 2 or 1? 1? Okay. Because there's only 1 GTDO card. If there was more than 1 on that chain, then I would use 1 or 2. But there's only 1 card, so it's always 1. On rack 1, we have 2 GTAO cards on 1 daisy chain. So there's card number 1 and card number 2. But for the GTDO, there's only 1 card, so it's always 1. And here assigned controls processor, number 1, corresponds to this box here, number 1. You may or may not have seen this component last time. We're going to use this switch here, a binary switch, 32-bit switch. And that should be all I need to compile. Oh, no. Oh, anyone know what my problem is? It says a request has been made to send an output to GTDO card number 1 on fiber port number 2 from RISC processor card number 1 and subsystem number 1. But it's saying there's no card there. If we look at the config file again, see rack 1, there's no GTDO cards, but rack 2, they're there. So I'm compiling on rack 1, so I need to change. And there's still a problem. This is a good error to see. Sometimes, if you only have a controls component, the compiler doesn't like it. So normally you'll have a large simulation case, so it'll be okay. But for this, we can just do something easy. And we just need to put a controls component, a different controls component in the case. So I'm just doing this. It doesn't actually do anything, but it should let me compile now. So it's a bit of a funny error. So I'll open a runtime for this case. So now I'm going to add my switch. So there's a normal switch, which, I guess that works too. But we can add it using this binary switch. And we can find it here, SW32. We can also choose a number of switches. So since I only have 16 bits, I'm only going to use 16 bits in runtime. You can also change the color of each switch if we want, but I'll leave them all as red. So here's my binary switch. So I can start my simulation. So right now, all the channels should be 0. Another thing about the GTDO card, it's actually not going to work the way I have it set right now. Because if we look at the hardware manual, so the GTDO card has 64 outputs, but it also has this extra terminal in the middle. So we have to supply it with external power from somewhere, usually 5 volts or 24 volts. But this one terminal supplies channels 33 to 64, and this other terminal supplies channels 1 to 32. So if we want, we can have 2 different voltage levels on the same card, but usually we just use 1 voltage level. We're also going to do a loop back, so we'll take the output of the GTDO card and bring it back into the GTDI. And as you may remember, the GTDI card has these resistors in it, and right now the resistors in there are for 5 volts. So we supply both 5 and 24. So we'll want to use 5 volt output from the GTDO. Otherwise, we'll burn the channels on the GTDI. So you need to be careful which resistors are installed when you're connecting to external controllers. So we have a cable here. If I can have a volunteer to connect the cable. So we're going to take power. One end of this cable has a connector like this, and we're going to take power off of the GT-FPI card. It's the front panel interface. All of the I/O cards have power connectors like this, and they're all 24 volts except for the GT-FPI. So we'll use this cable to connect the GT-FPI. Also, you can see there's 4 pins here. This cable only has 2 pins connected. The way it only fits in one way, and the way it's wired, you can't mess it up. So if you plug this into the 24 volts, you won't get any power, so it's okay. Do you know what those small screwdrivers are? Do we have one? No. RTDS one? Oh. So first thing when connecting things, turn the simulator off. GTDO. The bottom one is labeled GTDO.
This is the terminal for the supply input.
Yes. So it's a good practice to connect these first. Because if you connect this, then you have 5 volts, then you can. So the white ones go in here, and then one black one goes on here, one black one goes there.
This one black,
Yep.
white.
Yep, black.
Red.
Yeah.
Normally black is ground.
Black is ground, yes. All of the channels, the ground is common. So you only need to connect to one terminal.
And put this terminal on the top.
Yes. Nope, top one. Nope, they're not the same. You have to push hard. It's a bit scary. So all of these cards are 24, because you can see these. Yellow is 24.
24.
And this one's white, so it's 5.
5.
Yeah. So they come, this one is wired to this output here on the power supply, it's 5 volts. Yeah. And then one of these is, both of these are 24.
In GTDO card, it is a dry contact only, right?
No, the dry contact ones are on the front, because here we're wetting the contact. We're wetting it with 5 volts.
Yeah.
Yeah.
5 volts.
So when we do relay testing, a relay contact is a dry contact, right? Closed or open.
Yeah.
So typically we use the front panel,
Yeah.
but we can use this, but we have to supply a voltage, the 5 volts.
Oh.
Yeah.
Okay. Can I use the wire to jump for the active terminal to the relay for the external?
Sorry?
Because if I want to put the 5 volt that across the battery input of the relay, where can I see? Where can I find the minus voltage for the 5 volts? Or
Negative.
negative.
From 5 from 9.5.
It means that when the contact return output overhead, the 5 volt is sent to the wire.
No. Sorry. Okay, now I'm confused.
Yeah.
This is, we don't use this card.
Yeah.
That's output, right?
Yeah.
If we used it from the relay trip signal, we bring it to this one, input.
Oh.
Yeah, sorry. But then we would still, this isn't dry contact, so we still have to supply a voltage. We would have to supply maybe 5 volts to each terminal, right? So it sits high, and when the relay closes, then it shorts. So you can use it, but typically we use the front panel.
And what about for the digital output from the RTDS? That means that when the contact from the RTDS operates, the output voltage right to
The GTDO,
the end of the terminal.
No,
And the relay need to.
we wouldn't connect this to the relay
Oh.
ever. It's for controllers.
What is used for digital output of the RTDS?
The digital output it's controlled by the RTDS. So in runtime, those switches, I control it. So I choose whether it's low or high.
Oh.
So you would send that to a controller maybe, a controller outside the RTDS, but we don't use it for relay testing because the output, digital outputs, usually for relay you need a breaker status, right?
Yeah.
So we use that one down there because that's high voltage.
Okay.
We can only get
In the front
maximum
panel.
24 out of here. The front we can, again, we wet the contact with
Okay.
150 volts or 125, and then we can send that to the relay. Yeah. Okay.
ไม่ได้ใช้แค่ simulation จากที่
So the simulator's off.
แล้วมีผลอะไร
One other important thing, when we unplug the power, there's something we need to do afterward. So when we plug the power back in, and I try to turn it on, nothing happens. There's a blue button down here on the relay. We have to push it, and you'll hear a click. So when the power is cut off, that relay trips. So we have to reset it before we turn the power back on. Okay, now that the racks are back on, I can start my simulation case. So now if I set channels 2, 4, 6, 8 to be on, I can go and measure the voltage. 2, 3, 4, 5, 6, 7, 8. Two? Yeah. Card number? There's only one of them, right? So it's always one. And we can put it on the same processor as this one because it's connected to the same PB5 card. So I've only connected channels 1 to 8, right? So I'm only going to monitor 1 to 16. And I'm going to call it input. So now at runtime, I'll create a plot to monitor the inputs. So I have this. I'm going to make it a digital plot so I can see all the different signals. And then when I click down here, I can choose as bit pattern. And then if I want to see 8 bits, what should my mask be? It's a hexadecimal number. Remember before we only wanted to see 3 bits? We put 7. So what should I put for 8 bits? Sorry? No. So 3 bits, if you think of 3 ones, that's 7. What's the hexadecimal number for 8 ones? What's 4 ones? 1, 1, 1, 1 in hex. What is that? 7? 16? But it doesn't, it starts with letters, right? So what is it? F. So if 4 is F, what's 8? FF. So now I have my 8 bits. So if I refresh, they should all be 0. And if I start changing switches, now I can see my loopback cable is working correctly. Because the signal comes out of the GTDO and goes into the GTDI. Yeah. Sorry? Yeah. So you can see all the channels are connected properly. I'll show you here. So if I have in binary 1, 1, 1, 1, and I change it to hex, I get F. So that's what I'm doing for my bit mask to get the number of signals. So again in binary, if I have 8 ones, in hex I get FF. So this number down here is always a hexadecimal number. If I put 3 Fs for 12 bits, and I change 9, why is this not 1? Do you know why? I change these, this changes. But when I change number 9, it doesn't change. Do you know why? The cable has how many channels connected? Only 8. So channel 9 is not connected, so I won't see the change. Even though channel 9 on the GTPO card will be 5 volts, it's not connected to the GTPI. So I can't see it in runtime. Okay, so you guys can build a simple case like this one and try it out and see if you can make the loop back work. Oh, I'm actually going to do something that's not so nice for you. I'm going to change the fiber cables in the back. So you have to figure it out. You have to change your config file and figure out where they're plugged in and be able to compile and run. So I'll change those. You can also come and look once I've changed them. So RSCAD doesn't complain. I/O capabilities, and that's the low voltage panel. So I'm going to make a new case. I'll call it low voltage. So again, I'm going to use the controls library, and inside I/O components, we have the GTFPI component here. So inside here we have some options. You can choose to include the high voltage panel signals or not. I'm going to say no. So here we have the 16-bit inputs, or 16 channels of inputs, and 16 channels of outputs. So on the output side, I'm going to use the binary switch again. And on the input side, we'll just be monitoring the input. So again, I'm going to look at my config file and see where my GTFPI is. So you can see here it's on rack 1, and it's connected to port 2 of PB5 card number 1. So I'll use a processor assignment box, and I'll assign PB5 card number 1, controls processor number 1. So down here, assign controls processor is 1, so it should be okay. And port number 2. Again, 7-segment display. There's only one GTFPI card, so it's always 1. I can also choose to have input only, output only, or none, or both. For now, I want both because I'm going to use the input and the output. You can also choose to invert the input signals. This is for relay testing because typically, as you can see on the drawing there, the low voltage panel has a pull-up resistor on the input. So it sits at 5 volts all the time. So and it's a dry contact, so if it's connected to the trip signal from a relay coming into the simulator, when the relay trips and the contact closes, it shorts the input. So in our simulation, typically if we monitor, we'll see 5 volts or a 1 at the input. So when the relay trips, we see a 0. Sometimes for protection, we might want the trip to be a 1, right? To trigger breaker opening or something. So we can choose to invert the signals. Yes or no? So I'll leave it at no for now. Again, if I try and compile, it gives me a problem because I didn't change the port number. So it's kind of strange because this time it works without adding a multiply block. I don't know why. So I'll create my binary switch. Again, 16 bits. And I'll make a plot to monitor my input. Again, what should my bit pattern be for 16 bits? What should I use? Down here. FF? Just 2F. Yeah, 4Fs. Good job. I was wrong. Okay, so my simulation is running. And you can see here they're all 1, right? Because at the input, it sits at 5 volts all the time, unless we shorten contact. So if I take a banana cable here, and I go to channel 1, and the top one is input. If I do this, we should see a change in the simulation, but only if I update my plot. So you can see channel 1 went to 0. So an easier way to see this is to create a light as my input. Again, here's the hex bit pattern for 16, FF. So my lights are all on except for channel 1. You have to be careful a bit because channel 1 here is on the left side, but it's the least significant bit, so it's on the right side in runtime. So again, if I change it to channel 5, the channel 5 light goes off. If I, in draft, if I invert the signals, yes. Now all of these lights should be off, except for this one should be on. So I've just inverted the inputs. I can also do a loop back. So all of these channels are off. If I loop back channel 1 to channel 1, now I have channel 8 is, oop, what's going on? Why is high? Channel 8 on. Something strange. Okay, so now I can do a loop back from channel 1 to channel 1. So by controlling the output, I'm changing the color of the lights now. But the only reason we can do a loop back is because it's only 5 volts. Be careful when we don't usually want to apply a voltage to the input because we'll burn that resistor that's there if the voltage is too high. So you guys can build a simple case like this and try shorting the contacts or doing the loop back. We break for lunch, and then this afternoon, Dean's going to start with the relay stuff, so more fun stuff than what I'm doing. So the last thing I want to show, and it's on the agenda, is the cross-rack transmission line and the cross-rack transformer. So you have 3 racks, including the portable. So you can run, you don't have a global bus hub, which is needed for more than 2 racks, but you can still run a 2-rack simulation. If you wanted to make this 2-rack simulation more powerful, you could take the PB5 cards from the portable and put them in one of the racks to have 6 PB5s, and then you could run a simulation with 9 PB5 cards. So I'm just gonna do a demo for you now, because it's fairly simple. But with one rack, you can have a network solution with a maximum of 72 one-phase nodes. So that equals 24 3-phase buses. So we would count this as one bus and this is one bus. So this circuit only has 2 buses. So you could have a maximum of 24 buses on this processor with a network solution. With racks with PB5s in them, we can have 2 network solutions on 1 rack. So when we do that, 2 processors would be allocated for the network solution. However, with only 3 cards in 1 rack, you would have 2 network solution processor, 1 control processor, and then there's only 3 left over. And that's usually, it's not enough for components for 48 buses. With 48 buses, you'll probably have more than 30 transmission lines and machines. So there's not enough processing power to have all 48 buses. But if you put the 3 PP5 cards in the portable in rack 1, then you could have a full 48 bus network. So I'm going to show 2 different options of how to split the network. So when you have more than 72 nodes, we have to split the network somehow, and we do that at the transmission line. So you may remember from the first training that the transmission line needs to be a minimum of 1 time step long. So if the time step is 50 microseconds, and we assume the speed of light for travel on the transmission line, we wind up with about 15 kilometers. So if we use chapter 2 here, this line is default 50, so that should be enough to split. So in this case, we don't need to split. It's very simple, but I'm just showing you how we can do it. So in this case, there's 2 ways to split it. So here we see SS1 being subsystem 1. So I'm going to add a subsystem for subsystem 2. So 2 will run on the second rack. And right now, racks 1 and 2 are connected, so I'll use both of those for the simulation. So the first way to do this is I'm going to select this part of the circuit and group it and cut it and move it into here. And I'll try to compile. So it compiles successfully. So if I look at my processor assignment, this might not be the best way to do it, because in subsystem 1, I have my a T-line, a source, a network solution, and controls. In subsystem 2, I have a network solution and controls. So I'm actually using 5 processors for this simple network, which is way too many. But you can see that how it compiles. There's a network solution here because I have a bus over here. So this bus needs to be calculated by the network solution. You can see that the T-line is still in network 1. That's because we're in subsystem 1. Wherever this box is where the T-line is calculated. So we can actually move this back, and I can move this box into here, and I should still be able to compile. So now I have controls, network solution, only a source in rack 1, and rack 2 only has a T-line. So you can make a whole subsystem just with T-line boxes, and the physical lines can be in any different subsystem. I'm going to take this back over here. Now, because I have a runtime built from before, but now I'm using 2 racks, you'll see a couple of the plots aren't available. Because if I look at the plot properties, now I have 2 subsystems. So I've moved the fault component into subsystem 2. So then I have to go into here and now find it. So number of graphs 2, graph 1, I want LG, FLT, and graph 2, I want IAG. So now I'm able to monitor them because they're from another rack. So I should be able to run this in. This is on rack 1. with me. Does everyone remember how to unlock the rack? Right click, unlock rack, default password is RTDS. But if someone else is running a simulation, don't stop it on them. It's not very nice. There's a reset button on the bottom. If you're having problems, just hit that. Okay, so now my simulation is running and nothing appears different other than the fact that you're now running on two different racks. There's a second way to run on two racks, and we use something called the cross-rack transformer. So even though this is a transformer here, and you can find it in the power systems library under transformer models, and it's up here. So one side goes in one rack, and the other side goes in the other rack. And it has a calculation block, just like a transmission line. So in this case, we have a 10 kV source, transmission line, or transformer. It's not changing the voltage at all. It's going from 10 to 10. And even though it's a transformer, and this is what the other rack looks like, even though it's a transformer, it gets modeled as a transmission line. So the time step, the equation for the time step is equal to the square root of the capacitance times the inductance of the transmission line. So what we do with this transformer is we take the leakage reactance and we use this as the L for our transmission line, and then we automatically assign a capacitance. So we have to be careful that we don't add too much shunt capacitance into our circuit, because it's not real. We're putting it there and it's adding on to our network, but it's actually, unless there's an actual transmission line there, we have to be a bit careful. So we can actually, once we compile, we can view our map file and have a look at the capacitance that was picked for bridging the racks together. So again, you need to make sure that this leakage reactance isn't too small, because if it's too small, the capacitance that gets added is large, and it can cause some numerical problems. So, unless you, typically in a transmission system, you'll have a line that's long enough to split more than 15 kilometers. And that's about it for that, and I think everyone's ready for lunch.
going to look at Chapter 5 and quickly go through Chapter 6, and then we're going to look at Chapter 8b, which is controls component case that models a transformer differential relay. So introduce how you can build relay algorithms using discrete components. And then we'll look at a transformer model with internal faults, where you can fault a certain percentage of the winding. So if everybody can go to Chapter 5 in the tutorial. We have an induction machine model that is a three-phase, and you can operate this induction machine as a generator or a motor, depending on whether you have positive or negative torque input, or greater than nominal speed, or less than nominal speed. There's a torque input and a speed input mode, and depending on, as I mentioned, the value of the signal, greater or larger than nominal, it will either act as a generator or a motor. Inside Chapter 5, it introduces the parameters that are necessary to set up an induction machine. It gives references, and some of the references do not have saturation characteristics, so there's some default saturation data that is included in the model, but really with any type of simulation model, you have to have good data to get good results. Chapter 5 lists some references and gives some example cases, but just bear in mind that this is not meant to be an example that is used for every simulation. There's a section in here that shows a torque speed characteristic, and it's more or less just an example to show the torque versus speed curves that you can do with the RTDS. So this little circuit here just ramps up the speed. There's a reset and on-off switch, and you can generate different speed input and get the torque characteristic. So there's a couple of other examples in Chapter 5. There's one where it's built to do this torque versus speed characteristic, and the other one, which we're going to run, basically shows the operation of closing the breaker, picking up an induction motor, and seeing the huge current drop on the initial closing of the breaker. There's quite a bit of good information in here, and if you're really interested in induction machines, it's worth your while to go through it. And I know from before, you guys know where the draft cases are pre-built are already, so there's no point in asking you to build this, but you really should be able to open it up, run it, and understand it. So we have a source here. I think this is at 230 or 400 kV, 230 kV transmission line. 230 to 13.8 kV. Then a 10-kilometer distribution line. And then a transformer that would be feeding some industrial load, 13.8 to 400 volts. And then this would be some industrial motor. This little circuit here is just creates typical fan load. So depending on what the mode input is for this motor, you see this IND2T, that would be your mechanical torque input, and then IND2S would be a speed input. So I've already compiled my case for rack 2. You guys should be able to copy, assign to one of the racks, and it should compile. KAE is running on racks 1 and 2. Who's that? There's 4 racks. You don't need to take half of them. So the simulation starts here. We have our breaker open, so the induction motor is not connected. The speed torque switch is set to torque. It's running. There's very little power being sent from the source, and nothing they're basically nothing, 4e to the minus 9. So when we close in the breaker, you can see our voltages connected at the terminals of the motor drop. Huge inrush until the motor comes up to speed, the currents become normal, and then the voltages recover. So let's take 10 or 15 minutes. You guys can open up the draft case, examine it. If you have any questions, you can ask us or read the tutorial. But it's a fairly simple case, but it shows a good characteristic of an induction machine. The question was how to get different colors for the different voltage levels. The easiest way to do it is copy one bus, edit the color, I don't know why I'm choosing pink, but. Now, you could edit these different busts and then save them in your user library. So if you have a preset colors for different voltage levels, I would modify one and then save them in your user library. And then when you build a draft case, go to your user library. Does everybody know what the user library is? In draft, by default, the master library opens up. Now, you can go open library here. See this? And you have an option, master or user. Now my user library has a bunch of stuff in it just because I've been doing this for more than a decade. So, but typically the user library on brand new installations has very little.
โ
We're going to look at Chapter 6 and introduce the synchronous machine and controls. Chapter 6 is meant to introduce the user to the synchronous generator model and associated controls. Automatic voltage regulator, power system stabilizer, excitation system. And using these models allows you to look at the effect of the generator dynamics within your control loop. And it could uncover stability issues with the power system. You know, as long as your network and controls are modeled accurately. The synchronous machine model is a three-phase machine. Again, like the induction machine, generator if it's positive torque, motor negative torque, synchronous condenser with no torque. We have a single line diagram view and a three-phase view. The inputs and outputs are shown here. So we have TM. It's obvious, mechanical torque as an input in per unit. EF, field voltage, input in per unit. VM per unit, the generator terminal voltage. W, machine speed output in radians per second. And IF, which is the field current. So these would be going to your generator controls. And inside the RTDS master library, there are some predefined control models that typically you would use, or if you want to make your own, you would use the controls components library. An embedded unit transformer can be included in the model, and this would eliminate 3 extra nodes from the network solution. So the unit transformer, which is an option, you can set it up as Y delta lagging or leading. As I mentioned before, the exciter, ADR inputs and outputs, governor turbine model, and also this generator model can be used to take input from a multi-mass. So you could provide all of the different dynamics from like a steam turbine. So typically a hydro system is one mass, but you could use the multi-mass model to provide all of the different dynamics that you would see inside a steam turbine. And this is what it would look like. The machine parameters, the very first part here, paragraph, we say that the parameters required by the RTDS synchronous machine are quite standard and should be readily available. So electrical and mechanical parameters are very similar to stability programs such as PSSE. And there's a reference here which uses generalized parameters. And then each parameter that you see inside the generator model, there is an explanation of what is required for each parameter. I'm not going to go over every single parameter here. Now, the machine initialization and startup. This is part of that load flow. Remember, Cyprian introduced load flow where it goes through its iterations and back calculates the source voltage. What also happens with the load flow is it calculates all of the different parameters that need to be set inside the generator controls and sets up the controls so that the generator starts up stable. If you have a large system with multiple generators and lots of controls, and you do not have a stable load flow calculation at the start, your system probably will not be stable, because you would have to start the system and have all of the generators set into a lock mode. So the lock mode would make it operate like a source, and then you would have to adjust all of the slider parameters inside the generator to get the correct load flow that you want. So that's one of the other important things about the load flow, is being able to do this. Now, to occur. Because the load flow has no concept of what sliders or what needs to be done when you make your own external controls. As I mentioned before, this lock parameter is essentially what it does. It locks the rotor at a fixed position, and once the system starts up, you can release it, and if the system's stable, the machine will go into a steady state. The example case, everybody knows where to find it, chapter 6. Copy it onto your user folder, open it up, and we'll have a look at it. Is everybody on this have the draft case open? So a quick overview of this draft case. We have our source here. We have a double circuit transmission line here. Typically what you've been using is this T line with only one set of conductors. This and this are essentially the same. It's just optional parameters turned on. Of course, this requires more computation than this, but it's still using the same base code. So we have our double circuit line here. We have a breaker. We have one half of the transmission line. Then we have a bus here. And typically when we see a fault switch connected to a bus, we would call this a fault bus. But essentially it's allowing you to fault inside the transmission line. Because remember, you can solve a certain percentage of the total transmission line length here, and then put the remainder here. We have another breaker here, and then we have our synchronous machine. And we have an excitation system, a power system stabilizer, and our governor turbine. this example, it's using a set of controls here. There's a push button to set the fault sequence in progress. There's some pulse generators here that have some fixed times. So this signal here operates on the rising edge. And then the output of this is multiplied by a switch here, which, depending on the position of the switch, is going to have different bits enabled. Right? So this signal is going to be multiplied, and then this variable is going to be transferred into this fault branch. This timer here is labeled FCLEAR, F clear. So 50 milliseconds after the fault sequence is applied, this combination of timers resets the flip-flop. So this signal here opens the breaker, breaker 1 open, breaker 2 open. And then this reclose push button would be a manual reclose. So the user presses the fault sequence, the fault is applied, and then cleared with the breakers open. So essentially we have a source connected to the synchronous machine. We have a parallel line arrangement, and we have a faulted line. And essentially we're going to put the fault on, take out this third line, which would only leave 2/3 of the transmission line capability left inside this network. And this this example case will show how the system will go unstable and lose synchronism for certain fault sequences when the power system stabilizer is turned off. So in chapter 6 in the tutorial manual, pages I think 14 and 15, the last few pages explain this draft case. So you guys should be able to open it up, compile it for one of the racks, and follow the instructions in here. We have about 30 minutes for the rest of the day. I wanted to introduce transformer differential relay. It's in chapter 8B. This is an example of how to build a differential characteristic using controls components. So chapter 8B has quite a bit of information in here about the basic concept of differential protection. There's an overview of what this tutorial is doing. It's basically creating a two-winding differential relay that is a percentage differential with two slopes, slope 1, slope 2, some second harmonic blocking. So if anybody that has worked on a Westinghouse HU relay and knows that, understands the fundamentals of transformer differential protection, this should be no problem for you. There's some topics on differential protection consideration, magnetizing inrush, phase shift, tap changers, different voltage levels. And some conditions that cause magnetizing inrush. We'll go into this a little bit later on when we do a more complete example. I have one example that I provided that is a parallel transformer configuration where we have saturation on both transformers, and we can open and isolate the transformer and energize it and watch sympathetic inrush, that type of phenomenon. But this chapter is just basically meant to show how you would go about building a relay using controls components. We don't need to spend a lot of time with it. But essentially, this is what the controls components will end up creating for you. We're going to have our operating current, our restraint current, some minimum operating current, a slope 1, a slope 2, and then a high set. So basically anything in this region is your restraint. Anything above this is your trip. So the more restraint you have, the more operating current you need. I guess the idea behind the two different slopes was to account for CT saturation when you got into the really high fault through faults. There's some description on analog signal sampling. I'm not going to go into this. If you're interested, you can read. There's enough information. You should be able to figure it out. The relay settings, what I wanted to do was create this two-winding percentage differential relay with sliders. So instead of setting, entering a value inside the setting program, you would change slider values, and then the logic behind would create the minimum operating current, the slope 1 characteristic, the slope 2, the maximum operating current, and the second harmonic blocking. So essentially this is just the relay setting logic. So you would have a slider here that would provide your percentage of second harmonic blocking, a minimum operating slider, a slope 1, a slope 2, a restraint, a high set. And just by doing providing sliders and these gain blocks and multiplier, arc tan, you can create all of the necessary components to create your characteristic like this. So if you're really into protection and want to, know how you can do it, this is the interesting chapter for you. Earlier in my career, all I did was set relays and commission them, and then eventually I got into being able to build cases and figure out, how to make something work the way you know how it works in the field. This case is found, where is it found? Under Chapter 8B, Differential Relay. So we have a transformer here, Y delta. We have our CTs. We have some fault switches where we can fault on either side of the transformer, and then a fault switch that would be inside the differential zone, right in here. Inside all of these hierarchy blocks is all of the logic for this relay. Analog signal sampling, we have these components called the sampler. So essentially we feed in the 50 microsecond signal, and then this sampler, you specify the frequency, and it downsamples. It also can do interpolation. So if your sample rate isn't an exact integer of your simulation time step, it'll interpolate and output the correct sample point. So it samples at 96 samples per cycle, and then downsamples to 8 samples per cycle, and then it just ends up creating the downsampled delta currents. And I said normally you would have a low pass filter and anti-alias on your front end, because this is just a fake relay. We don't really need to do that, but normally you wouldn't do that. So you take your sample quantities, and in this case, I'm just using a 0 to 2 pi ramp. So this changes from 0 to 2 pi at 60 hertz. Now this signal is used to tell when the DFT should sample. So it's taking in the sample quantities, doing an 8-point DFT, and then outputting the fundamental quantities. So we need the A phase operate the fundamental, and we also need the second harmonic. So once you get your operating quantities, you have to do the same thing for your restraint. Here's that circuit to calculate your characteristic. And then we would have a percentage slope characteristic for A phase, B phase, and C phase. Pretty straightforward in here. You have your second harmonic, your fundamental, a restraint quantity, and then this if-else logic and this switch here just switches between the slope 1 and the slope 2. Second harmonic blocking, minimum trip. Here's your high set logic, sample and hold, and then an A phase trip. The circuit breaker control here, it is used to create a maximum inrush by trapping flux in the positive going direction when you open the breaker. So that when we close, we create a worst possible inrush. These reset flip-flops essentially just emulate an 86 lockout relay. So when your relay trips, typical for a transformer, right? When transformer protection operates, your lockout relay is set and you cannot re-energize the transformer without going out and doing a physical inspection. So that's all that this logic is doing to make the simulation a little bit more realistic. So that was the 10-minute course on how to model a transformer relay in the RTDS. It's a pretty interesting simulation because you can get right down into the details and look at the logic. I have not compiled and ran this case for a number of years, but it should be good to go. One thing with the transformer, you notice that this winding, the Y winding, has a bit darker line. This is a visual indication to me that saturation is enabled in this transformer model. So this is going to give us our inrush, right? The case is compiled, the transformer is closed. So if we open up breaker 3 and breaker 2, so breaker 2 is on the Y side winding. Now if we close breaker 2, we should see a transformer inrush. And if the relay is set properly, the second harmonic blocking should keep the relay from tripping when we energize. So we can see a lot of harmonic content in the waveforms. And our harmonic blocking signal was active. So I'll go and close in the other side of the transformer. So now we've got some load on it. I've got a dial here, so if I put it into position 2, we're going to have a 3-phase internal fault, and our 86 lockout relay should operate. These breakers should open. And nothing's happening. I don't know why. It looks like the CT is not producing any secondary current.
You know what? What? There's a bug. Oh, this is the, no, I thought, I had the same thing earlier this week. It's it's the power system. Yeah. That's why
the CT model is not producing any current. There is current flowing through the breakers, but something is not right with this version of draft case. So unfortunately, we'll have to figure out what's going on with it. For tomorrow morning, we're going to look at this other case. And there's a folder that everybody copied. It was called Second Training. There's a folder called Transformer. And inside this case, it essentially, we have transmission lines. We have a bus system here. And we have, hopefully these CT models work. Nothing works. I know this case used to work, and I'm not sure what's going on, but we'll go over this case in detail, but essentially we have a transformer here, a 3-winding Y delta Y transformer, and we have some loads here and some fault switches where we can put external faults on, we can fault the bus. And then inside this component, I'll introduce and explain in more detail what's going on here. But essentially, you see how this piece of bus is connected to the hierarchy box. Inside here is some single-phase transformer models with internal faults available. Because these are single-phase, non-load flow, we have an artificial load flow branch here that encapsulates the single phase, and all this is used for is to provide the right inductance and MVA and winding voltages to help solve the load flow. And then inside here is our single phase components, and then we also have a saturation branch which is used to provide the saturation routine, which is not included in these components. So we'll go into detail tomorrow and then continue on with the rest of the